All right, so weight and balance. Two things there. What are they? Weight and balance. They're two separate things. There's weight and then there's balance, okay? So when we talk about weight and balance, usually what goes in our head, what we're thinking about is the center of gravity and where is the balance point on the airplane. Okay, but we also need to think about weight. We need to think, we'll talk about that too. So we have a maximum gross weight that an airplane can weigh. It can't weigh more than that. In our cases, for takeoff, we call it maximum gross weight. And then where that weight is located in the airplane longitudinally is very important. Longitudinally being where it's located along the fuselage. Whether the weight's up here, whether the center of mass, where the point where you could say all of the weight is concentrated is up here or back here, or where, depending on where we load the cargo or the payload, where does the center of mass end up? That's the CG point, or the center of gravity, center of mass. That's really, really important, okay? All right. Why do we need it, first of all? When you guys load, anybody ever gone on a vacation somewhere in your car, you load your car up, you head out on the road? You ever think about how much weight you put in it and where you put it? Or you just throw it in there? You just throw it in there, right? You don't care. It doesn't really matter that much. Maybe if you trailer stuff, now you might care more about where you put the weight because it has to do with how the thing fishtails and all that stuff. But in the car itself, you got four wheels hitting the pavement, and you don't care whether you've got 1,000 pounds or 5,000 pounds, as long as the car's not squatting so much the wheels are hitting the rim, right? You don't care. You just throw it in there, you put it wherever you want to put it, and you hit the road. All right, you can't do that in an airplane. We cannot do that in an airplane, all right? There's a maximum weight. We cannot overload an airplane for reasons that you'll understand very well in the next 3 hours. We cannot overload the airplane, and we have to be very, very careful about where, when we put that weight in there, where does the center of mass end up, okay? So I want to talk about, before we even get into center of gravity, I want to talk about stability, because where the weight goes will speak to the stability of the airplane, okay? All right, so stability. What is stability? Stability. All right, there are two kinds of stability that we talk about with an airplane. Two kinds of stability. We have static stability, and we have dynamic stability. All right, so anytime we talk or anytime we think about stability in an airplane, we usually just say stability, but it's comprised of two things, static and dynamic. So I want to just briefly kind of go through that with you. And then each one of those types of stability comes in three flavors, if you will. All right, and they both have the same thing. You can either have positive, so you could have positive static stability, you could have positive dynamic stability, okay? You could have neutral, or you could have negative. Okay? So that for stability, I'll explain what these are, but from a stability standpoint, that's what we got. Every single airplane is designed by the designer and built by the manufacturer to exhibit either positive, neutral, or negative stability statically and or dynamically around all three axes. Okay, so for newcomers, just real quick, you have a longitudinal axis, you have a lateral axis, and we have a vertical axis. So the airplane rolls, pitches, and yaws. Those are the three movements that we have in an airplane, right? Around those axes, we have designed static and dynamic stability, and it is either positive, neutral, or negative around all three axes. Okay, so if you have, let's say you have positive static stability longitudinally this way, okay? It doesn't mean you have positive static stability laterally. It doesn't mean you have positive static stability in yaw. So all three movements have their own designed set or own designed stability characteristics. Okay? All right? They're designed by the designer and then built by the manufacturer to have that. All right? Now, when we load the airplane, okay, we can change that by the way we load it. That's very important to understand that. All right. If you're flying, when we're flying these airplanes that we fly, these general aviation airplanes, or if you get on the 737 to go visit grandma, okay, these airplanes are all designed, all of them are designed with positive static and positive dynamic stability around all three axes. Okay? And that's what we want. We want the airplane essentially to be a very stable airplane. Okay. How many of you want to go in the military and fly fighter jets? Nobody. One. Okay. Well, when you get in those fighter jets, that jet is designed to have negative static and negative dynamic stability around all three axes. In fact, it's so negative, you won't be able to fly it unless there's a computer attached to the controls. And if the computer goes out, you gotta eject, because the plane is uncontrollable. Okay, so that's the range when it comes to stability. You can have a very stable, very controllable airplane like we want, or you can have a very unstable, very uncontrollable airplane like you want when you're dogfighting. Okay, all right. And what happens between the stable and controllable and the unstable and uncontrollable in the middle is something we call maneuverability. So how maneuverable is the airplane? If the airplane is very controllable over here, so it's positive, 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 it's very, very controllable, it is not maneuverable. Now you might say, for those of you who've flown these planes, pretty maneuverable, pretty sporty little airplane, but you're not going to win any dogfights. Okay? On the other side of the spectrum, you have a very unstable airplane, very uncontrollable, but man, it'll whip around on a dime, and it is very maneuverable. Does that make sense? So that's the way we think about stability. We think about stability as positive, neutral, or negative. And on one end of the spectrum, we have a very stable airplane, very controllable, not maneuverable. On the other end, we have very unstable, very uncontrollable, but very maneuverable. And what everybody in this airplane, except for this young man right here, wants to be flying is this side over here. Okay? All right. In the middle, something that's more neutral is where you're going to find things like your aerobatic airplanes, those guys that do all the funky aerobatic stuff. Those are going to be more neutral in their design characteristics. Okay. All right. Let me put some meat on the bones to what this looks like. So let's just draw an airplane up here. Okay. All right, we have four forces on the airplane. Let's go back to week one. What are the forces that operate in that direction and that direction? Lift and weight. Okay. So I'm going to use this symbol right here as the center of gravity. That's the symbol I'll use. This is a symbol you see from an engineering standpoint. That's usually the symbol you get when they want to refer to the center of mass of an object. Okay. So whatever this airplane weighs, in this example, it's loaded such that all of that weight would be concentrated right through here. So that's weight right there acting in that direction. Another way to think about this is if I put this airplane up on a sawhorse and I balanced it, it would balance right there. It would be equally balanced right there. That's the center of mass. In other words, all of the weight on this side of that point equals all of the weight on that side of that point. So it's perfectly balanced right there. That's the center of mass, the center of gravity. Everybody with me? All right. With a positively stable airplane design, if you want an airplane that has positive stability, then the design of the aircraft and the design of the airfoil is such that the lift, the center of lift, just like if you take an airfoil, again going back to week one, when you take an airfoil, if you were to look at all of the separate little lift vectors on the airfoil, you might have lift acting, might look something like this. So that the lift kind of looks like that on the airfoil. But you'll have a point where you could say, just like weight, you could center all that and say if I was holding it by a string, the center of lift would be right here. Does that make sense? So you might have the center of lift where all of these would be concentrated, maybe somewhere right there. We would call that the center of lift. Okay, not to be confused with the coefficient of lift in that formula, but we call it the center of lift. That center of lift with a properly designed airplane is going to be aft of the center of gravity. So the center of lift is going to act back here. Everybody got the picture? All right, so we're pulling down here. We're pulling up there. Where's the nose going? Nose is going down. Nose is going that way. And we call that a nose down pitching moment. A moment, in engineering terms, is simply a rotational force. Moments are rotational. Okay? So what's happening is the airplane is pitching around the center of gravity. And by the way, all of the movements, when we talk about airplane movements, when we talk about pitch, roll, and yaw, guess where they center at? Right there. All right? So if the center of gravity were such that it were out here on the wingtip, when you rolled the airplane, it would do this. And when you yaw the airplane, it would do that. If the center of gravity were such that we're here, when you pitch the airplane, it would do this. And when you yaw the airplane, it would do that. So wherever the center of gravity is, and by the way, the center of gravity doesn't have to be located within the confines of the airplane. Center of mass of any object doesn't have to be within the object. Here, let me draw something. Oh, better yet. Let me hold something up. What are these? Where do you think the center of mass of those donuts is? You think it's within the donut? No. It's in the middle. Right? So the center of mass of an object does not have to be in the object itself. But wherever that ends up being, that's where the pitch and the roll and the yaw is going to happen. So this nose down pitching moment pivots around that right there. Okay. This is a positively stable airplane. Okay? So what keeps this from happening as we fly? This right here. That right there. That's a horizontal stabilizer. And attached to the horizontal stabilizer is the elevator, the moving portion of it, right? So we have a horizontal stabilizer and elevator combination back here that provides a force that way. And let's say that the amount of this force is 200 pounds. Well, this has to be 200 pounds to counteract it. And as long as we have that, now we have an airplane that doesn't do this. We're flying right along. These are like the feathers on the arrow, right? And by the way, if you look at the airplane just a little, what to do with it? Oh, here it is. If you look at it from this direction, instead of this direction, look at it from that direction, this is a vertical stabilizer. So what keeps the airplane going straight in yaw is that right there. Same thing that keeps the airplane stable in this direction. Okay. All right, so if this airplane weighed 2,000 pounds, okay, how much lift do we have to generate for this airplane to fly? 2,200 pounds. All right, so we have a load factor up here equals 2,200 pounds in this case. Everybody see that? I think it's pretty simple to grasp, right? Okay. All right. So what this means, I'm just going to leave that up there for just a second. So this is a kind of an example of what would be termed a positive, and this airplane would exhibit positive static and positive dynamic stability if it's designed like this, right? And this is the way All general aviation and transport category aircraft are designed. This is the way they're designed. They're designed to exhibit positive static and positive dynamic stability around all three axes. I'm just showing it to you in the pitch or longitudinal axis. I'll show you later how it works in roll and in yaw, okay, at the end, okay? I just want to get you to have an idea of what this is. All right, so having that in your mind, a picture of that in your mind, let's talk about static and dynamic stability, positive, neutral, negative, and what that means. So let's say that this is our flight path. I'll come over here and do it. Let's say this is our flight path right here. Okay, so we're just flying along kind of straight and level. And we're trimmed out. Everybody know what trimmed means? For those of you who haven't started flying yet, you may not know, but trimmed means that you take the control forces off the stick so that you can let go of in this case, the elevator, the pitch control. You can let go and the plane stays right where it's at. It's kind of like autopilot, sort of. Okay, poor man's autopilot. All right, so we're flying along and we grab the stick, we grab the yoke and we pull back. And what's going to happen when we pull back? The aircraft is going to divert up into that direction right there. And let's say we pull back and then right here, we let go. We just let go of the stick. What's going to happen next? Immediately. So what happens instantly or immediately in a very short period of time determines or defines the static stability of the airplane. So the airplane is going to do one of three things. It's either going to, as soon as you let go, it's going to want to attempt to return to where it was. It's going to want to have a tendency to just stay on that new path. Or it's going to want to have a tendency to divert from the path. Positive, neutral, negative. Okay? If the airplane is designed like this, we have what is effectively an airplane that wants to go nose down, right? So if I pull up and let go, it's going to want to positively correct itself. That make sense? The static stability speaks to what does the airplane want to do initially. When you disrupt the airplane in pitch, roll, or yaw, if it's a trimmed airplane, you can take your hands and feet off everything and it's just flying along nice and happy, and you step on a rudder and it does that, and then you let go of the rudder, does it immediately want to come back? If it does, it has positive static stability. If it just wants to stay out there kind of sideways like a dash hound running down the road, it has neutral stability and static stability in yaw. And if it wants to swap ends, it has negative static stability in yaw. Same thing with roll. You're just happy. You put a little bank into it and you let go. What does it want to do? Does it want to return? Positive static stability. Does it want to just stay right there? Neutral static stability. Does it want to get worse? Negative static stability. So what happens immediately after you make a control input, or you make some change to pitch, roll, or yaw? And it doesn't have to be you. It could be wind currents. It could be gusty conditions. It could be thermals, whatever. Something, you or the atmospheric conditions, upset the apple cart in pitch, roll, or yaw from a trimmed condition. What immediately or initially happens next will be static stability. Everybody got that? Okay, now let's talk about dynamic stability. So static stability is what happens initially. Dynamic stability is what happens after some period of time. Okay? So let's take this example here. Let's say the airplane does want to continue, wants to try and come back. It wants to correct itself, so it has positive static stability. Well, as it comes back down here, it's not going to get back to your altitude and then just go straight, right? It's going to descend below the altitude a little bit. It's going to build up some speed, which is going to cause some lift. It's going to cause it to come back up here, and then it's going to oscillate, and eventually the perturbations will go back to a trimmed condition. That would be positive dynamic stability. Okay, now it's not going to, probably won't happen at the same altitude, but what will happen is you will eventually end up back in a trimmed state, just like you were before the disruption occurred. Make sense? That's positive dynamic stability. If you had neutral dynamic stability, then you can imagine what's going to happen. All the way to Cleveland, or until people start throwing up. All the way. That would be neutral dynamic stability. And if you had negative dynamic stability, well, then it just gets worse and worse and worse until the wings and parts of the airplane start falling off. Okay? All right. Everybody understand stability a little bit? Okay. All right. If we have, so what we want, for purposes of this class, really what we want, and for purposes of most everybody in here, you want a positively stable airplane. You want an airplane that is controllable. You're not doing any dogfights, right? You want a controllable airplane. You want an airplane that you can trim out and you can let go. If you have an unstable airplane or even a neutrally stable airplane, it's very difficult to trim it. It's constant flying. You're constantly flying the airplane. You cannot trim it and let go. It doesn't. It wants to divert. It wants to go someplace else. Okay? All right. We can start with an airplane like this that has positive static and positive dynamic stability, and we can screw it up. We can turn it into an unstable airplane. And here's how we do it. We load it such that the center of gravity is not here. It can still weigh 2,000 pounds. Okay? But we load that weight. Maybe we put that suitcase, instead of the front seat, we put it way back in the back. Suddenly that shifts the center of gravity aft or whatever. So if you were to load this such that the center of gravity, well, let's say it was right underneath that, well, you're still 2,000 pounds. This would go away. Your wing loading would now be 2,000 pounds because you don't really have any tail down force. Does that make sense? Okay. So you don't have any nose down pitching moment. So you're basically balancing on the head of a needle, right? Can you kind of see that? So what we would have would be something closer to neutral stability. And you're flying it. You're just flying that thing, right? And if you loaded it back here, now we have that. Now we have an unstable airplane. Now we can go win some dogfights if we can live through the flight. If we can control the airplane. We have a totally uncontrollable, totally unstable, very maneuverable airplane versus a very stable, very controllable, unmaneuverable airplane. All based on where the center of gravity falls. Is anyone conceptually not grasping this? If so, please tell me, because we'll go deeper into it. Okay. Can you kind of sort of understand the reason why the center of gravity and how we load the airplane is important here? Okay. Center of gravity not only affects the stability and controllability and maneuverability of the airplane, but it will also affect the performance of the airplane. Okay? One of the things that we're going to talk about is weight. Weight is the biggest enemy of an airplane. Period. It's the biggest enemy. You want airplanes to be as light as possible. Weight kills airplanes. It just kills their performance. It kills everything about the performance of an airplane. And a lot of times people don't recognize or understand the correlation between center of gravity and weight. Well, let me show it to you. Right here, we have a 2,000 pound airplane. What's the load factor? 2,000 pounds. So this is, from a performance standpoint, well, actually it's not 2,000, because in this case you've got, let's call it the 200 back here. So you've got 2,200 pounds. This is load factor. This is what's going to the performance of the airplane, not that. How much lift I have to generate, how much load factor I have on that airplane. Okay? Well, if I move the CG way up here, such that I have a nose down pitching moment like that, and I got 700 pounds back here, now I've got 2,700 pounds. I've just added 500 pounds of load. The airplane's weight didn't change, still 2,000 pounds. But the load that the wing has to carry went up quite a bit. And that kills performance. It's just as if I had a 2,700 pound airplane that I'm trying to fly. Because that's essentially what I have. It's not just the weight of the airplane, it's also this tail down force that I need to keep it stable. Okay, and that kills performance because now I have a heavier airplane. I got to fly at a higher angle of attack, which means I have more drag. I'm going to fly slower. I'm a heavier airplane. I need a longer takeoff. I need a longer runway to take off on. That's a performance killer. I have a heavier airplane. I need a longer runway to land on. That's a performance killer. I have a heavier airplane. I can't climb as fast. That's a performance killer. I'm flying slower. I burn more gas. That's right. So this is all really critically important and related to performance, not just stability. Okay. Any questions on that before I move on to how we do weight and balance, how we calculate weight and balance? But I just want you to understand why we do it, why it's really, really critically important. Not just because the FAA says, well, we think you have to do this math as a pilot. Right? It's not why we do it. Okay. All right. Everybody have some scrap paper? Anybody need scrap paper? Raise your hand if you do. Everybody else good? All right. All right, get your pens, pencils out, get your calculators out, your phones. We're going to do some weight and balance. I'm going to show you how to do weight and balance calculations. All right. The first few examples, first few things I'm going to put up here have nothing to do with airplanes. They have simply to do with finding the center of mass of an object. What you're going to learn how to do today is find the center of mass, mathematically, of any object. Any object. A chair, a couch, your car, a donut, whatever it is. If you want to calculate where's the center of mass at, I'm going to show you how to do it. And then we're going to use that same formula to find the center of gravity or the center of mass of an airplane. Okay, same thing. All right, so there's a very simple formula. The formula is weight times arm equals moment. That's the formula. Weight times arm equals moment. Therefore, for those of you that remember, well, for me it was like 5th grade math, that would mean that moment, I could take this and I could rearrange it and say that moment divided by weight, let me do it this way, divided by weight equals what? Arm. Okay? You don't have to remember this, and if you can remember this one, you should be able to back into that one, right? But you can write them both down if you need to. Weight times arm equals moment. Moment times weight equals arm. So let's talk first about what those terms mean. Okay, so get that. Did everybody get a sheet when a handout? All right. Everybody get a handout. All right, so on that handout, let's go over these real quick. A couple of things. I will define these first. So an arm, what is an arm? The arm is the horizontal distance from the reference datum to the center of gravity of an item. Okay, so what does that mean? If I have a beam, just a wooden beam, let's say right here. Okay, and I say that I want to arbitrarily, I guess I gotta define datum. Look at the 4th item down there, the datum. See the datum? Let me define datum. Datum is an imaginary vertical plane or line from which all measurements of arm are taken. Okay, so let's just pretend that, and the datum point, in other words, the point where we begin our measurements, the datum, it's an arbitrary reference line. You can pick it. Anybody can pick it. The manufacturer picks it, the designer picks it, or the designer picks it in the case of airplanes. If you're doing your own weight and balance, whatever, you can pick it. It doesn't matter where the datum is. It just matters that wherever you choose to put it, you don't change it. All your measurements come from the same place. So let's just arbitrarily say this is going to be our datum right here. That's the datum. Okay? An arm is the distance from the datum. Okay? So let's say that the entire plank here is 20 feet long. Okay? And let's say that I were to put a weight, some kind of weight right here that weighed something. So this would be my weight. And whatever distance it is, this would be the arm. Okay? And if I were to, according to this, if I were to multiply that weight times that arm, I would come up with something called a moment. Remember, a moment is a rotational force. How much rotational force would be applied right here based on that weight and that arm on this object? Okay? All right. So weight, arm, and moment, and I've added datum, okay? So that we at least know what these terms mean. We'll come back and I'll talk about these more as we get into other stuff. All right, so let's do something real quick here. Just show you how to set this up. I'll leave this up without the weight on it first. And what I want to do is I want to calculate the center of gravity of this 20-foot long beam. Where do you think the center of gravity would be if it's 20 feet long? 10 feet. Pretty easy by inspection, we can look at it, right? So when you have an object that is like this, doesn't change its shape, it's pretty easy to just go to the middle and say, as long as it's made of the same material all the way through, pretty easy to go to the middle and say the center of gravity is going to be right here in the middle someplace. Well, you can't do that with this. The weight is very unevenly distributed, so you have to do something else to calculate it. So I'm going to show you how that works. I want you to set up on your paper a table that looks like this. You're going to put station. I'm going to define what station is. And then you're going to put weight, arm, and moment. So this looks familiar, right? Weight times arm equals moment. But in front of that, you're going to put station. I'll explain station. Station we're going to define, and it's on the paper here. Station is where you put something. Station is where you put a weight. So in the case of an airplane, let's say, a station would be like the pilot seat. A station would be the passenger seat. A station would be the baggage compartment. A station would be the fuel tanks. So anywhere you're going to put some weight is a station. And that station is what you measure, how far from the datum to that station. That gives you your arm, and then you can put the weight in there. Okay? We'll do a couple of these if it's sound confusing. Let's just figure out mathematically using this formula. We know that the center of gravity just by looking at it is 10 feet, but let's do it mathematically. All right. We need a station. Well, first of all, we need weights, right? So we're going to take this object and we're going to put a scale. Let's say we put it on a scale right here, and we put another second scale over here. So we weigh it here and we weigh it here. You can't weigh it in the middle. You got to weigh it on both ends. So over here, we'll call this the left side. And over here, we'll call this the right side. Those are our stations. So we have a left side and we have a right side. Well, how much does it weigh? Well, let's say it weighs 200 pounds over here, and it weighs 200 pounds over here. Okay, so the weight of the left side is 200 pounds, the weight of the right side is 200 pounds, so the total weight is 400 pounds. Pretty simple. So we know the whole beam weighs 400 pounds. All right, what's the arm? Remember, we said the arm is the distance from the datum to where the weight is located, or to the station. So what's the distance from the datum to the left station? 0. What's 200 times 0? 0. What's the distance from the right side? 20 feet. What's 200 times 20?
0.
4,000? 4,000? So it would be 4,000. In this case, it would be 4,000 foot-pounds. 4,000 foot-pounds of rotational force. So, in other words, this 200, if you just take this object and you put 200 pounds out here, it's going to want to have a rotational force of 4,000 pounds of moment. Because it's 200 pounds times 20 feet, 4,000 pounds of moment. This side, since we're measuring from here, has 0 rotational moment because it's at the datum. All right, now, so what is 0 plus 4,000? 4,000. All right, so we said that weight times arm equals moment, therefore, what's the next one? Moment divided by weight equals arm. So what is 4,000 divided by 400? 10 feet. There's your center of gravity. So the arm for the center of gravity is 10 feet, right here. 10 feet. So we could look at this and see it, but I'm showing you how you would calculate it. Okay? This is what we do when we do weight and balance on an airplane. Except that we don't have to go out and measure all this stuff. The manufacturer says, here's the airplane, here's the datum, here's the stations. All you got to do is put in the weights. They tell you what the arms are. You put in the weights, you multiply times the arm, you get this and this, you divide, boom, you got your center of gravity. It's a really simple thing. It's really not hard at all, but I want you to understand kind of the background of it. So if you kind of under the background of it, you're going to really understand it a lot better. It's just going to be like, okay, well, that's just a no-brainer. This is not a hard thing to do. Okay? All right. Let's make this a little bit more difficult now. Okay? We know that I'm going to erase this. We know that this plank, the empty plank, I'm going to call it the empty plank. I'm going to leave this up here, but I'm going to put a new set of data in my thing here. And what I'm going to do, I got funky. All right, I'm going to say, all right, one station here, I'm going to call it the empty plank. So I'm going to say the plank all by itself. So the empty plank, in this case, weighs 400 pounds. And I already know that its center of mass, its arm, the arm for that is at 10 feet, right? 10 feet. Therefore, the moment of the whole thing is what? 4,000, right? Let me erase this goo over here on the board. Everybody with me on that? Do you have a question? Oh, okay. All right, now we're going to put a person on this, and we're going to load up our plank, just like we load up an airplane. So here's our empty plank. No cargo, no payload, no baggage, no fuel. There's nothing on it. But now we want to put something in it and recalculate where the weight center of mass changed to. So let's say we put me over here. I weigh 220 pounds. I don't weigh 220 pounds. 210 pounds. Putting weight on myself. All right, and let's say that I stand, let's call it 18 feet over on this end. Just me. Where did the center of gravity move? And what's the total weight now? So we can start with our empty plank. We knew what the empty plank weighed. We knew where its center of mass was. And now we just add something to it. All right, what did we add to it? We added David. David weighs 210 pounds. We put him at 18 feet. What's 210 times 18? This is where you're going to get your calculators out because I can't do this in my head.
3780.
3780. 3780. All right. That's a 610 pounds. This is 7780 moment. What's 7780 divided by 610? What is it? 12.75. So the center of gravity moved this way 2.75 feet. It's now at 12.75 feet from here. Because all of my weight shifted the center of the balance to here. So before, with me not standing on it, this thing would balance on a sawhorse right there. But with me standing on it, we got to move the sawhorse over here, a distance of 12.75 feet, and now it will balance. We just moved the center of mass of the object. That make sense? Okay, now let's put somebody else on this thing, see where it goes to. Who wants to give up their weight? Go ahead. 165. Okay, 165. We're going to put William, we'll take this out. We're going to put William over here. He's 165. And we'll put him at, let's call it 8 feet. All right, now where's the center of mass? Now we got to put William in here. Let's put Will in here. He's 165. He's at 8 feet. Where's it at now? 165 times 8?
1320.
1320. All right, what's my total weight? All three of these added up? 775. What's my total moments?
9100.
9100. 9100 divided by 775. 1175-ish. So we moved it back 1 foot. So by him standing here, now we move this back a foot. Now the center of mass is here, 11.75 or 74 feet. You see what's happening? So every time we add weight to our empty plank, every time I say empty, I want you to think about an airplane with nothing in it, no fuel, no cargo, no people, no nothing. And then we start loading it up, and depending on how we load it up, the center of mass moves around, right? And that's what I was saying before with stability. If my center of lift is here, I want my center of mass over here. If it's over here, it starts getting neutral stability. If it's over here, it gets negative, right? So we want to load it so that we push that center of mass in the right place that the designer says. And we'll talk about this as we move on here. But you have a window. You have a range in an airplane. The designer says when you calculate the center of gravity, that center of mass has got to fall between here and here. And if it doesn't, you can't fly the airplane. You got to move things around until you get that center of mass such that you have a stable airplane the way I designed it. And you don't go kill yourself. That's why this is so important to understand this. Okay? All right, let's do another one. Let me start over and have you guys just figure one out from scratch, okay? You're going to use this same form here, same format. I'm just going to put, you're going to just put your own numbers in it. Okay. We'll start with the empty. We'll do the same empty, the same plank, okay? The empty we said was 400 pounds and it was 4,000, right? Arm, no, 10 feet, 4,000 arm. Okay. So we're starting with that. But let me do this. Okay, there's our empty plank, and it's the same one. It's 20 feet long. So the empty plank, we know what its deal is. It weighs 400 pounds. We know where its center of mass is. Because the designer of the plank did some weight and balance calculations on the empty plank, and they told us, hey, this plank that we're shipping to you, it weighs 400 pounds. And its center of mass is at 10 feet back from the datum. And they said, this is the datum. The datum is right here. They told us, the manufacturer of this plank said that's where the datum is. It weighs 400 pounds and its center of gravity is at 10 feet. So we know that information. This information on this first line, this empty plank information, we got that from the manufacturer. We didn't have to do that. They gave us that. But they don't know who we're going to put on that plank. So depending on who we put on that plank, now we change its total weight and its center of mass. So that's what we have to calculate. Okay, so we're going to put a weight right here. We're going to put a weight right here. And we're going to put a weight right here. And we're going to put these weights at, let's call that one 3 feet. This one is, okay, total to here, we'll call it 9 feet. So it's not 9 from here, it's total, okay? And then we'll call this one at 18 feet. Everybody with me on how this working? Okay. All right, and we're gonna put 500 pounds over here. We're gonna put 300 pounds here, and we're gonna put 150 pounds right there. Calculate the center of gravity. Okay, and from a station standpoint, you can call them whatever you want, but I just call this 1, 2, and 3. That'd be an easy way to set it up.
What's the weight?
So you got 300, 150, 500. And I promise you we will turn these into actual airplane weight and balance stuff here in a minute. Just want you to get the hang of it. Yes. You got it? Okay, hang on a minute. Don't spit it out yet. I want other people to, we'll see if everybody comes up with close to the same thing. How many of you have ever been on a little commuter airline?
Is that a 13 or is that an 18? On the
Where are we at?
3.
This is an 18.
Oh, it's an 18?
Yeah. So this is 3 feet, 9 feet, 18 feet, 300 pounds, 150, 500.
Okay.
How many of you have been on a commuter type airline? So on the regionals, on the bigger jets, this doesn't really happen as much. It could if it's a very lightly loaded airplane. But on the regional jets, it's not uncommon to get on, and once everybody's loaded, someone comes along and says, okay, I need you to move to this seat. You go and move to that seat. What do you think they're doing?
Adjusting weight.
They're getting the weight and balance right. That's what they're doing. All right. What do we got? What's the center of gravity?
11.3.
Everybody, who disagrees with that? Everybody got that? 11.3? Okay. Well, I'm not going to go through the calculation, and I believe you. It's probably 11.3 if all of you got it. Okay. Is this hard? Not hard, is it? Okay. All right. Let me do one more before break. And I'm going to just let you guys figure this out on your own, the whole thing, okay? I'm going to draw a plank that is not a rectangular square-shaped plank. Draw something like this. And we're going to find the center of gravity of this, the empty weight of this plank, okay? I will give you some things to go by. I will tell you that it is 50 feet long. Okay. We're going to weigh it over here, and we're going to weigh it over here like we have to. We're going to say it weighs 300 pounds over here. 300 pounds. And it weighs 50 pounds over here. Where's the center of gravity of this? Now I'm going to give you a hint, okay? You get to choose where the datum is. You can put it wherever you want, but wherever it is, make sure as I start adding weights to this, you don't change that location. Okay, I see most of you are done. What'd you get? Huh? Where's the center of gravity? Okay. You got, what'd you get? You got 2,500. That's your moment.
The moment.
Divide the weight into the moment.
By weight will give you the arm.
Yeah, and that'll give you the arm. What is it?
50.
How many?
50.
1, 5? 15?
Just 50. 50.
Oh, 50. So you're saying the center of gravity is at 50 feet? Right here? 50 feet?
So it's, like I got 7.14.
7.14? Somebody else got 7.14? You got 7.14? Who got 7.14? Who got something different than 7.14, but that is somewhere in the middle of this thing? Nobody? Everybody got so? Okay. Did everybody put the datum right here? Okay. Because if you put the datum somewhere else, you'd get a different number than 7.14, but it would still equal the same location. So I'm going to show you right now in the next 5 minutes why where you put the datum doesn't matter. It only matters that you always measure from the same place. All right. So everybody got 7.14 when you did the other. Okay, 7.14. So that's somewhere. Let's call it right here. Well, no, it'd be further back this way. If that's 50, be 25. Be somewhere in here. Right. Somewhere in there would be the center of gravity. Let's move the datum. Let's move the datum out here. "20 feet. This is now our datum. Okay, I'm going to show you why it doesn't matter. So we move the datum to there. And let's do this problem. Okay. Now we have left, we still have left side, or what I'm going to call left side, and right side. I don't know if that's what you guys called it, but whatever. All right, so we have left side and right side, and the left side weighs 300 pounds, and the right side weighs 50 pounds. The arm for the left side is now 20 feet, and the arm for the right side is now 70 feet. So 300 times 20 is going to be what, 6,000? And 50 and 70 is going to be 3,500? Okay, so that's 9,500 divided by 350 is what? I'm going to say it's going to be 27.14. What's that? 27.15. So from here, if I go 27.14, I get to right there. See why it doesn't matter where the datum is? When I calculate it this way, I end up with 27.14. So if I go from here, 27.14 feet, I end up in the same place. So it doesn't matter where the datum is. But wherever the datum is, you can't change it. Take all your measurements from that datum. Once you start the problem, once you start the thing, if you say this is where my datum is, it's there forever and ever, amen. Right? As long as you do that, you still end up in the same place. Question?
No, I answered it.
Okay, all right. All right, we're gonna do this one more fashion to just show you something else with the same guy here, same plank here. We're still gonna have left side, right side, which weighs 300 pounds and 50 pounds, but we're gonna change the datum again, and we're gonna show you it still ends up right here, but this time I'm gonna put the datum right down the middle at 25 feet. So the datum now is 25 feet, right in the middle. Okay? All right, now watch what has to happen. Anytime you measure to the left, it's a negative. Anytime you measure to the right, it's a positive. It's very important to understand that, because when you do weight and balance calculations on airplanes, some airplanes, many airplanes put the reference point or the datum point at the firewall or maybe the leading edge of the wing. And therefore, if you're adding or subtracting weight from the engine, it's a negative number. If you're adding weight here, it's a negative number. If you're adding weight here, it's a positive number. So you have to recognize that when you're doing your weight and balance calculation. So let's do this one. In this case, the left side arm is negative 25 feet. And the right side arm is 25 feet. So 300 times 25 negative is what? 300 times 25? It'll be the negative part. 7,000, negative 7,500. And 50 times 25? 1250. Okay, do the math on that. 1250 minus 7,500 is going to be a negative something. Negative 6,250 divided by 350 is what?
Negative 17.85.
So we go negative 17 point whatever, and we end up right there. See what I mean? Doesn't matter where the datum is. Okay, any questions? Anybody confused? Even a little bit? Even a little bit? Please tell me. Okay, let's take a break. Okay, so let's move this conversation into actual airplanes and how it affects airplanes. So every pilot operating handbook is going to have a weight and balance section, and if the airplane was built, certificated after, well, I think it's the mid-70s, somewhere in the 70s, they, don't hold me on the exact date, somewhere in the 70s, they standardized the POHs. So every POH after that date, Section 6 is weight and balance, Section 5 is performance, Section 4 is normal operating procedures, and so forth. They're standardized, so you can always know where to go in every manual, every POH or owner's manual, if you will, to find information. So I want to go through some of the way the POH, this is for a Cessna 172, but they're all pretty much laid out kind of the same way. And we'll do some things here. So you have, there we go. So here's a diagram that you'll find in most of them that just kind of shows you, this would be more for like the maintenance technician if they wanted to reweigh the airplane. It shows you how to set up the scales, where the datum point is at, how to do the calculations to find the empty weight of the airplane. All right, so remember when we were doing the plank thing, I kept referring to the plank as an empty plank, okay? And what I said is, okay, the manufacturer of the plank told you this is how much it weighs and here's the center of gravity. Well, with an airplane, it's very important that we have the manufacturer tell us, hey, this airplane, this one, not a generic 172, let's say, but that 172 that's sitting out there on the ramp, November 12345 Bravo or whatever, serial number 1582, whatever, that particular airplane, that one right there with the red and white paint and the leather seats, and the G1000s, not the 1975 one over here that's all clapped out with fabric seats and round gauges. This one over here weighs this much. And that one right there, its center of gravity is here. It's very important. That's a 172, that's a 172. That one doesn't weigh what that one does. That one's center of gravity is not where that one's at. Does that make sense? Just because they're both 172s, I promise you they don't weigh the same. Their center of mass is not in the same place. All right? So it is critically important that we as pilots know where to go to get some very key information. That key information is this first line up here, the empty information. In other words, the empty weight of that airplane. What's its weight? Where's its arm? And what's its moment? And well, you only need one of these. If you have one of these, you can calculate the other, right? Okay. So you need the weight and you either need its arm so you can calculate the moment, or you need the weight and you need its moment so you can divide and get the arm. You need one of these two pieces of information in an empty configuration for that airplane. Okay? All right. Go back to the list, the terms here. Let's talk about empty weight. Down towards the bottom, we have right in here, we have a number of definitions. We have standard empty weight, basic empty weight, license empty weight. Okay? Essentially what you're typically going to find, but it's important that you understand which one you're dealing with, but what you're typically going to find is a standard empty weight. The standard empty weight of an aircraft is the weight of the aircraft without passengers, baggage, or fuel. Standard empty weight usually includes unusable fuel and full operating fluids and full engine oil. This is typically what you're going to find is the standard empty weight. But sometimes you'll find the licensed empty weight, which does not, in some cases, give you like engine oil and engine fluids and things like that. And that's where you'd have to go back and put how much oil do I have, what does it weigh, and that would be a negative usually on your weight and balance calculation. Makes sense? Because it usually would be to the left, as you're looking at the diagram, would be to the left of the datum. Typically, datums are, but not always, you got to look at the manufacturer. Typically, the datum is going to be somewhere on Cessnas, it's always pretty much at the firewall. On our airplanes, the Remos is at the leading edge of the wing, right at the fuselage. That's the datum. So any weight, as you're looking at the plane, any weight this way would be a negative over here, a negative arm. Any weight this way would be a positive arm. Make sense? Some manufacturers will put the datum at the tip of the spinner. If they put it at the tip of the spinner, all your numbers are positive. So you just have to it doesn't matter, right? I showed you, it doesn't matter where the datum is. Just know where the datum is, and now you know how to do your calculations, and don't change it. You're always measuring from there. All right. So empty weight. the way we're going to define it and the way most GA airplanes define empty weight now would be your standard empty weight. So that is going to be the airplane sitting out there on the ramp with no people in it, no baggage in it, no cargo whatsoever, no fuel other than unusable fuel. Who doesn't understand, because I want to explain it, if you probably don't know what unusable fuel means. Anybody else not know what unusable fuel means? Unusable fuel is, unlike your car in an airplane, the fuel tank is designed so that there's a low spot where fuel can get down to that you cannot get to the engine. It's designed as a little sump. It's called a sump. And any contaminants in the fuel drain down into that area, and then with a little tester you can drain that. You can drain the tank and get water or debris out of the tank. And it's below the pickup. So if this is my fuel tank, here's my, usually they're in the wings, but not always. If that's my fuel tank, there's a little low spot right here. And there's a little area you can drain it out. So the pickup going to the engine might be here. So the engine can't get any of this fuel down here. This would be unusable fuel. We can't get to it. It can't get to the engine. So when you run out of fuel, you still have some fuel in the engine. In the tanks. That's unusable fuel. So empty weight is going to be the weight of the airplane with no people, no passenger, no cargo, no passengers, no fuel other than the unusable fuel. All of the engine fluids. So full oil, full coolant in the case of our airplanes, because we have liquid cooled engines, right? That's the empty weight. That's our empty plank. And then from that, we add people, we add cargo, we add fuel, and we do our calculations over here to figure out now where did we move that center of gravity so that we know that we have a stable airplane. Okay. Let's move down the line here. I'm going to just get to some stuff here. This is kind of an example that's turned sideways of, it's basically, you'll notice it's kind of the table that we laid out. Right? It's kind of what they're doing. There's just ways to calculate. I want to get down, here we go. So here's an example of how a Cessna 172 pilot operating handbook in the weight and balance section would give you. Here are the stations for a typical whatever year 172 this is. I forget what model. I think it's an R model, whatever it is. I don't remember now. But in this case, station, in other words, the arm, the distance back, you have pilot and passenger stations, and they are located somewhere between 34 and 46 inches aft of the firewall right here. The reason that it's 34 to 46 is those front seats in a Skyhawk slide on a rail. You can move them. So you could have it all the way forward, you could have it all the way back. And if you have it somewhere in the middle, what they're saying is if you're not sure, use 37. Okay? If you're a really tall guy, you might want to use 46. If you're really short, you might want to use 34, right? I mean, you figure out kind of what you want to use. If you're sitting in the back seat, this doesn't move. That's 73 inches. So whatever weight you put in the back seat of this airplane, whatever weight goes over here, it's 73 inches. So if you got 200 pounds in the back seat, it's 200 times 73 that's the moment for the back seat. If you put baggage in baggage area 1, it's 95 inches behind the datum. That's the arm. If you put it in baggage area 2, it's 123 inches. And the very back of the fuselage before where the panel is at, if you take the panel out, you're looking into the fuselage with the cables and stuff. That is 142 inches behind the firewall. Okay? So the manufacturer, you know how we set our thing up here? We set up our table, and we have stations. You can't see it now, but stations over here. So you got station, you got weight, arm, moment. The manufacturer already gives it to you. They tell you what the stations are. You don't get to choose. I think I'll put this at 23 inches. You're putting the weight here, 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 or here. So all you got to do is say, okay, I'm putting it here, so, and how much weight am I putting there? Oh, that weight times 95, that's going to go somewhere on my list here. Okay, and you add them all up, add up all your weights, add up all your moments, divide, there's the center of mass. That's where it's at now. Okay, but it's really important. Pilots, or when you're learning, you make this mistake, and some pilots make the mistake. You have to make sure that the first or it doesn't have to be first, but somewhere in this list, you have to have the empty airplane. You can't just say my weight, your weight, and our cargo and fuel. I mean, you could do the calculations that way, but it's not going to be right because the airplane, you got to add the airplane into that. Okay? All right. So we'll do a few here. All right, so here's another view. So this one was kind of the top view. The other thing I want to show you here is it doesn't show you a station for fuel on here. It shows it up here. You got to read it up here. The fuel on a Cessna 172 is located in the wings. So if you read the note up here, it says usable fuel CG arm for integral tanks is located at station 48 inches. So somewhere right in here is where they're saying the center of mass of the fuel tanks are, 48 inches back. Okay? So a lot of times the fuel tank isn't shown on the diagram. You got to read someplace where that's located. All right? And then this just kind of shows a side view that's not as usable for us from a weight and balance standpoint. But this could be. This is showing you inches aft of the reference point of the fuselage, how big it is and where things are. Okay, this is a sample loading problem. I see confusion here all the time when I start getting into stage 2 checks with you guys. Stage 2 is your pre-solo cross country, so you've already soloed, but now you're getting ready to go cross country by yourself. And I want to see that you got a weight and balance done, and you can do weight and balance. Okay, then and also on stage 3 when you're ready to take your check ride, and I want to see a weight and balance, right? I want you to notice that for this Skyhawk, it's got all the stations, right? You got your basic empty airplane, right? You got fuel, you got pilot and front seats, you got rear seats, you got baggage area 1, baggage area 2, right? And then they're adding all that up and all these things, and they're calculating. This is a sample. And recognize when you're looking at the manufacturer's, or you're looking at the pilot operating handbook, and all of them are going to have a sample that looks something like this. Make sure you know what you're looking at. What are we looking at here? They're saying that for this example, the empty weight of the airplane is 1,639 pounds. And this isn't giving you an arm. What's it giving you? A moment divided by 1,000. So the moment is actually 64,400. And if you want to know the arm, you got to divide 64,400 by 1639 to get the arm. So be careful that you know what you're looking at in the sample, in this sample problem. But what I see, let's say I'm doing a check ride with someone in this 172. Oftentimes I will see them come to me with a weight and balance, and they will tell me that the weight of the airplane is 1,639 pounds. What do you think the likelihood of that 172 that we're going to go fly weighs 1,639 pounds? Just about zero. So what they did is they just went to the pilot operating handbook and looked at, oh, well, that's the empty weight. No, that's not the empty weight. This is a sample. This is a sample. You have to go get the actual empty weight. The actual empty weight and the actual moment or arm so that you can calculate the other, right? You have to go get these two pieces of information from someplace. Where do you think you get that from?
Weight and balance sheet.
It's in the airplane. You got to go to that physical airplane. Open it up. Go to the documents in that airplane. What documents are required by law to be in every single airplane? And if these documents are not in the airplane, that airplane is unairworthy. What are those documents? What's the acronym?
Aero.
ARO, A-R, sometimes another R, O-W. What's the W stand for? Weight and balance. The weight and balance document has to be in that airplane. What information do you think we're going to find on that weight and balance document? We're going to find the weight and the balance. And that information, the weight and the balance for that airplane in its empty state, no passengers, no pilots, no fuel, no cargo, no nothing, is what we put in our thing here and here, or here. So this first line of information, this empty weight of the airplane information, we cannot get it from here. Where do we have to go? To the airplane we're going to fly. Pull the documents out and find it. Now we can do a weight and balance calculation for that airplane. Make sense? You wouldn't believe how much confusion there is about that when I do stage checks and check rides with people. Unbelievable amounts of confusion. All right. This is nothing but a sample. Okay, don't use the sample for your actual weight and balance calculations when you go fly, right? Just like you and your front seat passenger probably don't add up to 340 pounds, right? That's a sample. That's a sample. This is all sample. Okay. Okay, so let's see. All right, let's do a few. Let's just do a few problems here. We're going to go back to this right here, and we're going to do a few weight and balance, actual 172 weight and balance counts. So get your sheets out.
Question.
Yeah.
So with the sliding seats,
Yeah.
is the difference between 34 and 46 negligible?
Well, no, it's not negligible. Okay, it's going to change the moment, and the big thing is the moment change. So a little bit of weight. So one thing to conceptualize here as it comes to weight and balance, especially on an airplane, is if I take, remember we're calculating the CG, right? And the CG is what divided by what? Moment divided by weight. So the bigger the moment, the farther aft the CG is going to go, right? The bigger the moment. So I can take 10 pounds and put it at 37 inches, and I have a moment of 370. Or I can put 10 pounds and put it at 100 inches, and I have a moment of 3,700. So it's not a lot of weight, but moving it back here makes a big shift in the center of gravity, right? So the farther aft we go, the less and less weight we want to put back there, because it really makes some effect. So the point I'm making is the closer to the center of gravity range or window that we have to work with, the better off we are. Let's look at, before we do this, let's look at a range real quick.
And that makes sense. I guess my question is not whether or not the numbers are negligible, but like if I'm doing pre-flight, do I have to go out there and measure
No.
how far back I sit
No,
the chair? That's
no,
what I'm trying
no,
to get.
no. I wouldn't worry about that too much. But what you could do is this: you could take your weight, and figure out what the moment change. What's the moment difference? What's the moment? Your weight times 34 versus your weight times 4, or what's the difference? Or 8 inches? No, 12 inches. That's 12 inches. Your weight times 12 is what in moment, and that's how much moment is change is.
Makes sense.
You know what I mean? Is affecting that. All right, I'm going to back up just a little bit here and actually go back to. Oh, going the wrong way. Trying to find where it's going to give me. Let me find it here. Yeah, I'll go to the graph. I can go to this graph right here and get the information that I want. Actually, I'll go to that graph right there. So by using that, I'll explain these graphs to you a little bit later, but by using these graphs, I can find two quick pieces of information that I need. I can figure out what's the maximum weight this airplane can weigh. If I go right up here to the top of the limit, it's going to be 2,450 pounds. See that? 2,450 pounds. That's the maximum weight of this airplane, 2,450 pounds. So I know right away I cannot have this airplane weigh more than 2,450 pounds. That's my max gross weight. Okay? And I know that my envelope from a center of gravity standpoint is going to be from 35 inches to about 47.5 or so. See that? Okay, so I've got from 35 to 47.5. My range is 37 to, what did I say? 47.5-ish, somewhere in that neighborhood, right? So that's my range. So the manufacturer is telling me this information. It's also written somewhere else in there, but I know I can go to these charts and find it real quick. But as you thumb through that section, you'll also see it written down. All right, so what does this mean? Go back to your weight and balance terms thing here, and let's talk about these terms real quick. The maximum weight we talked about already. Well, we talked about the maximum empty weight. If you go to underneath the empty weight, you have maximum landing weight, you have maximum ramp weight, you have maximum takeoff weight, and you have maximum gross weight, or just maximum weight. See all those? The only one in general aviation that we really care about too much is the maximum weight, or the max gross weight. And that means that for this particular airplane that's 2,450 pounds, that means that you can take off at that weight, you can fly around at that weight, you can maneuver at that weight, you can land at that weight. That's the maximum weight. If the airplane weighs legally, technically, 2,451 pounds, it's an unairworthy airplane. And you're not supposed to be flying. You got to take some weight out, one way or the other. Johnny, you can't go, you got to get out. Or you got to drain some fuel out. Somehow or another, you got to get the weight at or below the maximum gross weight. All right. The other weights that you see there will come into play when you're flying bigger, heavier aircraft, like a transport category aircraft as an example. So you could have maximum, if you look at maximum takeoff, maximum ramp, and maximum landing weight. Maximum ramp weight's typically going to be the heaviest the airplane can be. So that's designed so that you can load that thing up with fuel. Get all your, say you're flying to Europe, and it's got a lot of fuel in it. So they load that thing up with fuel, and they're up to their maximum ramp weight. But that's heavier than their maximum takeoff weight. The idea is they burn some of that fuel weight in the taxi and all the stuff they got to do, and then they're a little bit lighter. Now they're at the weight where they can take off. Now they have their maximum takeoff weight. But they can't land at that weight. The maximum landing weight is a lot lower than that. And that's designed, that's there because they're going to burn a lot of that weight off as they fly, and they get the weight down into the landing weight that they can work with. We don't have to worry about that in small GA airplanes. We have one weight, maximum gross weight. Okay? All right. So that's the weight that we're talking about. All right, let's look at the range. Look up towards the top. You've got definition of center of gravity. Let's see. All right. Just below mean aerodynamic chord, it says CG limits or CG range. Let's look at those two. CG limits, center of gravity limits. That's what this is. The center of gravity limit is that you have a forward limit of 37 inches and you have an aft limit of 47.5 inches. So if I go back we'll look here. The forward limit is 37 inches, so basically right about here, and the aft limit is 47 inches. So the limit forward and aft is going to come somewhere right in here. So the center of gravity, when you calculate it, when you come up with your center of gravity, your calculation needs to end up somewhere between 37 and 47 and a half. If you do, if the center of gravity is somewhere in that range, you're okay. Your center of gravity is in a place where your stability is not going to get wacky on you. You're still going to have a stable airplane, stable, controllable airplane. If you get the center of gravity too far forward, you're going to be very, very nose heavy, and that has its own set of problems, which I will talk about at the end. And if you get the center of gravity on the aft side of that, that has a different set of problems, which is even worse, because now you have an unstable, uncontrollable airplane. And that'll kill you quickly. That'll kill you quickly, okay? So neither one of them is good. But if you're going to be a little out on one direction or the other, go forward, don't go aft. Okay? All right. So center of gravity limit is forward limit, aft limit. Range is, what is that? 12 and a half inches. So the range here is 12 inches. The limit's 37 to 47. Make sense? Okay. All right. So let's just do some stuff here. I'm going to I'm going to move this over so it's not behind that. I'm going to set up a new chart here. All right, so station, arm, or excuse me, weight, arm, moment. All right, so the first station should always be what? Empty weight. Empty weight. All right, and then we can go pilot, front seat, or whatever, however you want to say that. Passengers. And then you can go, that's rear passenger, let's go rear. Rear seats or rear passenger. Bag 1, bag 2. And fuel. Right? That's all the stations that are available to us in a Cessna 172. For this model Cessna 172. That's it, right? All right. We know that the front seat and rear seat passenger, or front seat and a pilot and front seat passenger, we're going to use 37. Let's just use 37. So we know that the arm is 37 inches. We already got that. The rear seat passengers, if we put any weight back there, is 73 inches. We know that. If we put anything in baggage 1, it's going to be at 95 inches. If we put anything in baggage 2, it's going to be at 123 inches. And the fuel is going to go where? 48 inches. Okay? So now we have it set up to do exactly what we were doing with those wooden planks. We just have to fill in the weights and then do the math. Okay. Let's look at these asterisks. What are those asterisks for? Arm measured to center of the area shown. So if you put your weight, let's say you have some substantial weight back here, if you put it up close to the back seat or you put it closer to, you know, the 108 inch point, you might want to then do a better measurement, because the farther back you go, the more critical that becomes. This one isn't as critical because the pilot and front seat passenger are basically located on the center of gravity. So little movements aren't going to make a big difference. Weight will make a bigger, the weight you put here will be the bigger issue, not whether your seat's at 34 or 46. The weight you put here will matter because it's 73 inches back. The weight you put here makes a huge difference because it's 142 inches back. Does that make sense? Understand that, right? It's that lever arm thing. The bigger the lever arm, the more force it's going to have. The bigger that arm, the more force it has. All right. So we'll use what the sample was here just for giggles on this. So we're going to say the airplane weighs 1,639 pounds. So the empty weight is 1,639. And where did we get this from? We went to the airplane. We got it from the weight and balance document on the airplane. All right. Somebody tell me what the arm is.
$39.2.
39.2.
39.3.
39.3. Okay, and everybody understand how he got that? He just simply divided 64,400 by 1639, because this is a moment, and it's a moment divided by 1,000. So let's look at this real quick. Divided by 1,000. When you're looking at these in the pilot operating handbooks, when you're looking at these samples, or you're looking at graphs, which we're going to show you here in a little bit as well, a lot of times the moments will be divided by 100 or divided by 1,000 or even bigger numbers. And the reason for that is so that when you're doing the math, you're not working with a number that is 64,400, you're working with 64.4. So if you did all of these, if you add all these up, you come to 106.2, right? But if you want to find the center of gravity, you don't divide 106.2 by 2450. You divide 106,200 by 2450. The only reason for doing the division here is to get these numbers small so that when you're doing the math on these, you're not putting in a whole bunch of zeros. But when you get to the bottom, you got to add those zeros back in. You understand? When you're dealing with Airbus A380s and you're talking about millions of pounds, right? You're talking about moment divided by a million. Otherwise, when you're adding those things up, you got, a whole bunch of zeros you're adding every time. That's the only reason we do this. Okay, so we know then that the moment on this is going to be, and we can just do this divided by 1,064.4. Right? If you think about it, the reason the sample is given this way is because do we really need to know what the arm is? For the empty weight? We really don't. All we need is this, because this is what we're adding up. We need this and we need this. Right? Okay. Let's say that we have 300 pounds of pilot and front seat passenger, and we have 300 pounds of rear seat passengers, and we fill the thing with fuel, 48 gallons. Now watch what we're going to do here. I'm not going to put 48 here because the fuel doesn't weigh 48 pounds. I have 48 gallons. I have 48 gallons. All right. Take your sheet again, your sheet that we're looking at. Look on the back of that sheet, and you'll see some weights down there, standard weights. These are good. Certainly gasoline is one to remember. Gasoline weighs 6 pounds per gallon. Okay, 6 pounds per gallon. When you start flying jet engine aircraft, that's Jet A is 6.8 or 7 pounds almost. Jet B is 6.5. Oil, if you're operating an older airplane where you have to calculate the weight of oil, oil weighs 6.5 pounds per gallon, not per quart. Per gallon. So if you're putting 2 quarts in, it's 3.75 pounds, right? So you have to do that math, okay? All right, and then water weighs 8.35 pounds. Why do we put that in there? Why do you care what water weighs? Well, look at the weight of water versus the weight of fuel. If you have your airplane sitting out on the ramp, this happens a lot, the fuel filler cap is right here. Well, if it rains and your cap doesn't seal real well, what do you think you're getting in your fuel tank? Water. Where's that water go? It goes right down here into the sump because it weighs more than fuel. Now you take your little tester and you drain all the water out before you start the engine up. Yes, sir. Just, what do you need? Okay. All right, so fuel weighs 6 pounds per gallon. So we got 48 gallons. The other fuel, the empty fuel, the unusable fuel, that's in this weight up here. So we don't have to worry about that. We just have to worry about the unusable fuel. So we got 48 gallons of unusable, of the usable fuel. So 48 times 6 is what? 280. 280? 288. Okay. Let's do the math. Let's see if we have a legal airplane.
Let's see. Did we ever sign bag weights?
No bag weights. No baggage. And as you're calculating your, I'll just tell you something. If we divide this by 1,000, as you're calculating your moments, just divide it by 1,000. So 300 times 37 is what? What'd you come up with for that first one? 11,000 what? What? 300 times 37 is 1,100? 11,100, so go 11.1. That way when you add these numbers up, it's quicker to add, then you just multiply it times 1,000 down here. That makes sense? You don't have to. You could do it full out and just add up a whole bunch of string of numbers. It's up to you. I'm just showing you why they do this. Just it makes it easier to add this string and then you just do one multiplication at the bottom to get it back to what it needs to be. What's 300 times 73?
21.9.
2129?
No, 21.9.
21.9. 21.9. 288 times 48?
13.824.
13 point, can we just say 13.8? Okay. Everybody get, is that what everyone's gotten? All right. What's our total weight? 25 what?
2527.
2527. Are we underweight? Nope. Okay. What's our moment?
112. Triple one. And then
2.
2 0 0.
111,200.
I didn't divide that.
Okay, 111,200. Okay. All right. Just for giggles, I know we're overweight, but are we within the center of gravity range? This way. What's a CG here?
44.
44. Okay. A little to the back side, but we're within the range, so we're okay. All right. But we're overweight. Let's talk about why that weight matters so much before we correct this. Talk about why it matters. 2450. If that airplane weighed 2,500 pounds, would it be unable to fly? Would it be physically too heavy to fly?
No, not necessarily.
Absolutely not. It'd fly perfectly fine. It would fly perfectly fine at 2,500 pounds. And as a matter of fact, I'm gonna posit to you that if we went and flew this plane, there'd be no way that we could fly it and not get the wing loading up or even beyond 2,500 on a regular flight. Okay? Because remember, the reason that the designer gives us limits, weight limitations, is not because the airplane won't physically fly at that weight or beyond that weight. It's because when we fly, we induce additional load on the airplane simply by maneuvering. We turn the airplane, we increase wing loading. When we turn the airplane, we're increasing the load on the wing. So let's say that we have an airplane that weighs 2,000 pounds. So we add our numbers up and our gross weight ends up being 2,000 pounds. We're well within the limits of the weight, right? If we go take that airplane, if you remember back to week 1, aerodynamics, if we take that airplane and we go into a 60-degree bank turn and we hold altitude through that turn, how much does the airplane weigh now? What's the loading? What's the wing loading now? It's 2,000 pounds like this. Well, let's say there's 200 pounds of down load on the tail. So we have 2,200 pounds of wing loading. 2,000 here, or 2,000 here, and another 200 here, so 2,200 that way. Right? Everybody with me? Then we put it into a 60-degree bank turn, and we hold altitude through the turn. What's the wing loading now? Huh? 4,400 pounds. We doubled the load on the wing. Every time you maneuver and turn the airplane, anytime you do this real quickly or you turn and you hold altitude, you increase the loading on the wing, right? I'm not going to get into why that is right now. You have to remember back to aerodynamics, okay? And it'll come back around. Aerodynamics will come back around. But whenever we maneuver the airplane, we induce centrifugal load, centrifugal forces. So the maximum gross weight of the airplane isn't because the airplane can't structurally handle it. It's because when we induce additional loads, we can quickly overstress the airplane if we start at something that's heavier than it needs to be. Does that make sense? It's not like loading your car. You put whatever you want as long as the wheels aren't, rubbing on the rims. A lot of people go down the road that way. You can't do that in an airplane. You can quickly and rapidly bend things, break things, bad things happen. We've got to maintain weight and balance. We got to stay under our gross weight limits so that we don't endanger ourselves while we are just simply flying the airplane. Okay? All right. So what are we going to do about the weight? Simplest thing would be to take fuel off. That'd be the simplest way. So how much weight do we got to lose?
27.
How much? 27 pounds?
It's 25.
About 77 pounds.
77 pounds? Yeah, because we got to go to 2450.
Oh, 25.
So 77 divided by 6 is about 12 gallons? Oh, no. 6 gallons?
Yeah.
About 13 gallons.
13 gallons? Okay. So we need to get down to about 35 gallons. If we went down to about 35 gallons, we don't have to redo this. You can all see how that would work out. If we were within limits here, then we're going to be within limits when we reduce weight. Okay? Does that make sense? So in a lot of cases, in many cases when you're flying aircraft such as Cessnas, especially if you're renting, when you finish flying, you usually don't, unless the airplane's left out on the ramp or something like that, or it's cold because you get condensation buildup in the tanks and then you get water in the tanks. Usually we don't top off the tanks because we don't know who's flying it next. And we don't know what, usually when you're flying, this is where we adjust weight. Or at least we pay a lot of attention to that because look, you and your significant other are going, and maybe you got somebody, kids or something going, and you got some luggage, and you might be kind of bound to that as much as you can. This is where you can adjust some weight sometimes. Okay. While we're on the subject of weight and balance, I'll tell you, how many of you want to own an airplane one day? Okay, good. That's good. It's fun. I own 6 of them. Good luck with that. All right. All right. Here's the thing you want to know. Go back to the terms. There's a term, I think it's on the back. It is on the back. The third up from the bottom. Useful load. That's the most important term that you need to really understand what useful load means if you're going to buy an airplane. Useful load. Useful load is exactly what it says. It's what's usable, what's useful to you as the operator of that airplane. So if you take the maximum gross weight of the airplane, let's say it's 2,450 pounds, if it's a Skyhawk, of this particular Skyhawk, let's say it's 2,450 pounds. That's maximum gross weight. And then you're looking to buy this airplane. And you ask the owner, what is the empty weight of that airplane? And they say the empty weight of that airplane is 2,000 pounds. That means your useful load is 450 pounds. That means that airplane's not very useful to you. Because once I get in and the passenger gets in, I can't put any fuel in it. I'm over gross. Okay? So the bigger the useful load, the more useful the airplane is. The more passengers and cargo and fuel you can put in the airplane. The useful load is the difference between what's the maximum gross weight per the manufacturer and how much does this airplane weigh. That airplane, not what it says in the pilot operating handbook that I can buy off of Amazon. What's it say in that airplane sitting out there with the leather seats and G1000s and the whiz-bang things that this pilot put in because he had to have this, that, and the other? What's it weigh, right? Useful load's important. So that being said, I will tell you that airplanes aren't designed like cars. Airplanes, for the most part, there are very few exceptions, but this is pretty much a truism, kind of an axiom in aviation. If the airplane has 4 seats, you can put 2 people in it. If the airplane has 6 seats, you can put 4 people in it. Adults. So if you're flying a Skyhawk, you can have 2 adults and some baggage, or you can have maybe 3 adults and some baggage, or a couple of adults and kids. But you're not going to load up a 4-seat airplane with 4 grown adults and baggage and full fuel. You'll be overweight. You don't even have to do a weight and balance calculation. You're going to be overweight. All right? So just understand that. All right. Okay. Let's look at, I want to show you something else here. We're going to use the same, I'm going to show you the graphs now. Actually, I don't want to get into it yet because we've only got 5 minutes before the next break. I'll show it to you in the next hour. Let's just talk a little bit about, go back to the importance of why we do this. When you're flying something like what we're training in, 2-seat airplane, right? The useful load on these airplanes is after fuel. So if you fill it with fuel, you top it off with fuel, your useful load with full fuel is about 500 pounds. That means you and I can get in the airplane and fly, and we're under gross weight. If you and I got in a Cessna 152, which is a 2-seat airplane, we'd have to drain all the fuel out of it to be legal to fly. All right, so useful load's important, okay? And when you're flying an airplane like this 2-seat airplane, there's only 2 seats. You got very few stations. You got the pilot and front seat passenger, you got the fuel, you got those little hat compartments right there, and that little compartment in the back. That's it, right? And all of it is located pretty much in the CG range. So it's very difficult, almost impossible to get that airplane out of CG. You could overload it. You could put 300-pound people in there and it's with full fuel and you're overweight. But your CG is probably still going to be within the range, okay? Well, the point I'm trying to make is, remember I said in the beginning that the FAA says we have to calculate a center of gravity. We have to do weight and balance calculations every time we fly. I do not get out a piece of paper and do a center of gravity and weight and balance calculation every time I get in one of those airplanes. Because I know those airplanes. And I know that unless I'm looking at someone that looks like they weigh over 300 pounds, I don't even care if it's filled. I know that it's okay, right? Because I understand that particular airplane. All right. When you get into, but there's 2 seats and it's right on the CG. But when you get into an airplane with 4 seats like this Cessna, and now you start having bigger moments because the arm of that back seat is quite a ways back from that CG, and baggage 1 and baggage 2 are even farther back. Or now you get into something like a 6-seat airplane. You had better be thinking about weight and balance. That's not something that you can arbitrarily just do in your head. That's something that you might have to do every time you fly. Okay? All right. That make sense? Okay. If you ever want to see, anybody here ever been to Oshkosh up in Wisconsin? It's the last full week of July every year. Okay. If you ever get a chance to go, you should go. It's amazing. The last full Monday through Sunday, whatever the dates are of July every year. Sunday, I went for 32 years in a row. Sunday, I would go and I'd sit my chair up on the flight line and I'd watch the departures. It's hot, it's July, it's humid, and everybody's trying to get home, and they load their airplanes up. Not only they were overloaded when they got there because they had all their camping gear. Everybody camps out by their airplanes. They had all their camping gear, they had all their stuff, and so they were probably at gross or maybe even a little over gross when they got there, and then they bought a bunch of crap while they were there. Now they're really overloaded, okay? And the scariest thing is watching those guys take off and they're just wallowing off the runway, and you can just see that they've got aft CGs, the CG's way off, they're overgrossed, they're barely clearing the trees at the end of the runway. It's serious stuff, guys. It's serious stuff, right? Okay, let's take a break. All right. When you take your written test, when you go to take your written tests, they're changing them a little bit. So, and they're actively changing them. So currently they have a book you can buy that has all of the things that you might see. Let me give you an example. As far as it relates to weight and balance, and other things as well. But as an example, let me see here, weight and balance. You could get a diagram on your written test that might look like that, and that's pertaining to weight and balance. And it has a center of gravity graph here, and it has some other information on calculating weight and balance. Okay, or you could get the table format like what I'm showing you right here. You could also get, you know, something like that, which again is useful load and weight and moments for a particular airplane. And they may ask you questions and to refer to this diagram to come up with the answers, okay? That's all changing though. They're changing the written tests and they're making them more dynamic and more scenario based so that it's harder, it's increasingly harder for you guys to go to study guides and memorize and then go take the test and pass it. They're making it more dynamic where you're gonna get something you've never seen before, okay? So that's much more important that you really understand what's going on, because then it doesn't matter what you get, you can answer the question, okay? My point for saying that though is it doesn't matter how they present the data. If you understand in the background what we're doing when we're trying to calculate the weight and balance, if you understand that we're just ultimately, when you do weight and balance, you're doing the weight of an object times its distance back from some arbitrary measuring position, the datum or the reference line. So that times that's going to equal that, and that divided by that's going to be equal that. So if you get all your list and you add up all your weights and you add up all your moments and you do the division, you're going to come up with the center of gravity of the entire system. Okay, notice adding these arms doesn't work, right? That doesn't mean anything. You get all your weights and all your moments, and then you do one final division problem and you come up with your center of mass of the system. This is the center of mass of that. This is the center of mass of that. This is the center of mass of that, right? But to get the whole system, you add up all your weights, all your moments, and then you divide and you get the center of mass of the entire system, right? Make sense? Okay. When you get to your test, or you get to an airplane that has a different pilot operating handbook that maybe doesn't give you this, they give you a bunch of these, it's the same thing. If you understand what's happening, you can use graphs, you can use tables, you can get out a piece of paper, you can do it this way. You're going to end up with the same thing because now you know how to do it, right? So I want to show you how we would use this chart or this graph along with, back to here. So we would use this graph along with that graph or that graph to do the same thing, exactly the same thing that we did here. Okay? And we'll use this same setup right here. We'll use these same numbers. Okay? I'll show you how to do that. And if these scare you, don't use them. Do that. If you don't want to do that, do that. It doesn't make any difference. We're coming up with the same thing. All right. All right, let's go through how this works. Okay. So this is a load moment, and notice that it's load moment divided by what? By 1,000, divided by 1,000. So look at these lines coming out of the origin of that graph right there. What do those lines represent? Stations. Every one of those lines is a station with the exception of what? What station's missing? Empty weight. Because the manufacturer of this Cessna 172 has no idea what the empty weight of your Cessna 172 is or where its center of balance is. But it can tell you that, hey, I'm the manufacturer, I'm the designer, therefore you can only put weight along that line or that line, or that line, or that line, or that line. That's the only place you can put weight. That's what they're telling you. Okay? So let's take this chart. The only reason for these is so that you don't have to get out a piece of paper and do this. You can use these and come up with the same answer that you would if you got out a piece of paper. So let's go through that. All right. How much does the pilot and front seat passenger weigh? 300 pounds. So we're going to come up to 300 pounds right there, and we're going to drop. Right down to there. And what's it come to? 11? 11, yep. All right, so pilot and front seat passenger, notice, is 11. Notice that? Okay. Rear seat passenger is 300 pounds. So we're going to keep on coming over here to the rear seat passenger right here. Then we're going to, my arm gets in the way, we're going to drop straight down to what looks like 22. Let's come over here. Pilot and rear seat passenger, what is that? 22. Pretty close, isn't it? Okay. Fuel, now we're overweight, but we're going to use it. 288 pounds on the fuel. So 288 pounds would be, let's see, 250, 60, 70, 88, would be almost 290. Let's just go to 290 to the fuel right here. Am I dropping down the right line there? Yeah. I'd call that 14. Okay, come over here, look what we got. 14. And we went to our weight and balance data in the airplane, and it told us 39, it told us 64.4. So let's add these up. Somebody add up 64.4, 11, 22, and 14. This marker's not writing very well, so I'm gonna go back to blue. What do we got? 111 times 1,000 is, pretty close. Okay, see how we use the graph to not do the math? Okay, so we come up with 111. Let's just keep the 111 so we don't even have to add the zeros to it. All right, we got 111. And we know our weight because we just told, we came up with the weight, right? So we know the weight. Now we got that 111 moment. Now we go to our moment graph. Now we go to the next graph. Okay. Here's our moment graph. And we come over here and we find our weight, which is 2527, which is already overweight. Oh, I gotta move this down a little bit. Now, I'm gonna have a hard time doing this unless I shrink it. There we go. All right, 2527. So we're overweight. So we're up here somewhere. Somewhere up here at 111, 120, so 19, 18, 17, 16, 15, 14, 13, 111 is right here. We're outside of our envelope. We're illegal. Okay? But let's say that our moment was 111, but our weight was 2,400. Well, then we would be in our envelope and we're legal.
What's the difference between utility category and normal?
I'll explain that. I'll explain that. Okay? So does this make sense? So we just did everything we did before, it's just we just used those graphs and it was a little bit quicker, wasn't it? All right, it was a little bit quicker. But if you don't like that, you can still get this out and do the same thing. So it doesn't matter whether you get a piece of paper out and do it this way. Weight times arm equals moment. Moment divided by weight is going to give you your center of gravity of the whole system. Or you go to that, come up with all your moments, put your weights in, come up with your moments, add your moments up, come down here, you have your weight and your moments, connect the lines, and as long as you fall inside the center of gravity moment envelope, you're okay. All right. Another graph is this one here, And this one works if you did it kind of by hand. So you did it by hand and you said, okay, let's pretend we came up with 2,400 here on the weight. You came up with 2,400 and you came up with 111. Well, you come up with, or excuse me, I'm sorry, you calculated your CG, which was what, 30, what'd you guys say it was, 37 or something, or 30? What was it?
At full, 44.
44, let's say it was 44. Let's say you were 44 and the weight was 2,400. So you go to your 44, and you go up to 2,400, same thing, you're inside the envelope. So whether you know the weight in the moment or you know the weight and the CG, you can use one of those two graphs to figure out whether you're okay or not. All right, let's look at the utility category and what that means. If you have an airplane that has a utility category, what that means is that when you're loaded, when your weight and balance calculation puts you in the utility category limits, well, first look at what it does. It takes your overall limit, oh, I erased it. Takes your overall limit from 2,450 and a range of 35 to 47 and a half to 2,100 and a range of 35 to 40 and a half. It tightens your range, your limits, and it lowers your max weight, okay? That allows you to do some limited, in this particular plane, aerobatics. It allows you to do things like spins, so you can spin a 172 as long as it's loaded in the utility category. So you have to weigh a little less, and you have to tighten up your CG range. Okay, so utility category enables you to impart more stress, more load on the airplane before something breaks. That's what that is. That's what that means. Okay? All right. That make sense to you guys? All right, let's do one using just these. Actually, how many people we got in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got enough. Okay. Okay, in the back of this, the very back, like when you open it, you see that, that's kind of the front. Go to the very back, and you're going to see a portion of Section 6 weight and balance. Yeah, all right, that's fine. If you find the graph, you're going to find those three graphs. These three graphs we were just looking at. Find those three graphs. They're towards the back of that. Yeah, it's the last 3 pages. That's the last 3 graphs that we had up here. So let's do some weight and balance calculations just using those graphs. Okay? All right. So we're going to say we have we'll go empty. We're going to go pilot, passenger, bag 1, bag 2. Fuel. Okay, so we're going to say empty is 1,700, and let's call, I'm just making stuff up here, so I don't know whether it's going to work or not. We'll find out when we do the calculations. Let's call the moment on the empty 65.0. 65.0, this is moment. Okay, because when we're using this, we don't really care about the arm because the arm is getting calculated automatically. All we're coming to is the moment, right? Okay, so we're going to say the moment is 65. Let's say the pilot and passenger are 250. Let's say we got a couple of kids in the back seat and together they weigh 150. Let's say we got 50 pounds of baggage and we got 30 gallons of fuel. All right. Does it work? Are we legal? We're already overweight? No, we're okay. Well, 3 times 6 would be 180 pounds of fuel. All right, so what we're going to do is get our moments and our weights. Okay? So now you could take this information right here that I gave you. You could calculate the weight and balance by just setting up a table and doing this. You could do that. Or you could use these graphs right here. You're going to come up with the same thing. All right. 250. So 250 on the pilot and front seat passenger. Let's go here. I'll drop that down somewhere in there. Call it 9.5 maybe. 150 on the passengers. $11. 50 on baggage 1. $5. 180 on fuel. $9. Does that look like what you guys got? Something like that? All right. So what's our total weight?
2,330.
2330. So we know we're good there. What's our moment?
I got 99,500.
99.5. Everybody agree with that? Okay, so now we go to this graph. And we plug those in. 2330. 2330 is going to be along this line right here. And our moment we said was 99.5. That's going to be right at 100. We're good. And we're in the normal category. So we can't go do spins. See how that works? I see confusion. Okay, what's your confusion? That's all right. What? Say it again.
For this, how did you get the arm?
So I didn't get the arm. I got the moment.
I mean,
So you get that right off of this chart here. So this will automatically calculate your moment. So all you have to do, where's my, what do I do with my thing? All you have to do here, Maggie, is take, so these are all my stations, pilot, fuel, rear, baggage, all that. So I know my pilot, this information here I got from where? Where'd this come from? Where'd that come from?
I'm sorry. I think I got confused on where the moment, how you got the moment.
That's what I'm going to show you. So first of all, where did I get this weight and this moment? The airplane. Remember, I have to go to the airplane to get this information. The empty weight information, the weight, the moment, arm, any of that, I have to get that out of the airplane itself. It has to come out of the airplane. You can find it nowhere else. Okay. This information, the stations for this particular airplane, the only stations available for the Cessna 172 are a pilot and front seat, passenger bag 1, bag 2, and fuel. Those are the stations. I know when we're going to go fly this airplane, I know that the way we're flying it, we got 250 pounds in the front seat. We got 150 pounds in the back seat. We got 50 pounds of luggage in baggage 1 location, and we're putting 30 gallons of fuel, which is 180 pounds. So I know that, all right? And I can add up my weights to 2330. Now I want to find the moments. Well, the pilot and front seat passenger are 250 pounds. So here's the pilot and front seat passenger line. 250 pounds to here, straight down, is 9.5. So that's my moment. So it's 9,500 really, but it's 9.5 because this is divided by 1,000. Where does it say that? Right here. Okay, all right, and then the passenger in the back seat's 150 pounds. So 150 pounds right here, come all the way over to the passenger line, all the way to here, drop that straight down, and you're at 11. So you have a moment of 11. See that? Okay, and then you take your baggage area 1, which is 50 pounds, so you take 50 pounds over to baggage area 1 and drop straight down, and you have 5. See that? So by using this graph, what we're getting is we plug in the weights and it gives us the moment. And then we take that and that data, which we knew the weight, and we add these up. Now we have to add our empty weight to it. We get 99.5. All these numbers are 99.5. Then we come to the next chart right here and we connect those lines, 2330 and 9950. 2330 right in here, 9950 right in here, and we find that we're squarely within the normal category weight and balance envelope. Okay?
That's just your weight.
Weight and balance. That's both. Here's your weight.
Because that automatically.
Here's your balance.
Consideration where the center of gravity.
Yeah.
Okay.
Because here we're finding whether or not we're legal using weight and moment. Here, this next one, we're using weight and CG. Right? So you can use either one. It just depends on how you calculate. So if you were to do the calculation this way and come up with your weight and your CG, you would go to this one. You wouldn't really need to because you know the limits of the airplane. You know you're within the right. But you could go here and figure out where it fell. And so if it fell at 44 whatever, you could also see, hey, I'm on the front edge or I'm on the back edge. And it doesn't matter. Look, if you're loaded right here, you're legal. If you're loaded right here, you're legal. If you're loaded right here, you're not. You just need to be in that envelope.
Would you fly that close to being?
Sure, I'd fly it right on the envelope. Yeah, sure. You're going to have a stable airplane. You're going to have, when you fly the airplane in the CG range, then the performance, which we're going to be getting to performance here in a few weeks, aircraft performance, you can expect, once you factor in atmospheric conditions, you can expect the performance of the airplane to comport to what the POH says. When you fly outside of the range, guess what you become? Anybody want to take a guess? When you fly an airplane, let's say you fly this airplane and the aft CG is back here somewhere or up here someplace. Guess what you have become?
An uncontrolled airplane.
You have become a test pilot. That's what you become. You become a test pilot. They don't have long life expectancies, in case you weren't aware of that. You're a test pilot when you do that, because now the manufacturer isn't going to guarantee you anything. They can't tell you how the airplane's going to perform. It's not going to perform. It's not going to do the things that it says it should do in the pilot operating handbook. It's going to be a different airplane than what the airplane was designed to be. So you are now, by definition, a test pilot. Okay? But when you fly within the envelope that the airplane is designed to operate within, then you can expect what the performance data shows in the pilot operating handbook. Okay? Okay, any questions? What did I do with my, oh, under here. Any questions on that? All right, I want to go back to, I'm going to get away from this a little bit. I want to go back to stability a little bit, and I want to draw some diagrams up here and show you why the airplanes are designed. What is it about the design of the airplanes that gives it the stability characteristics? We talked about stability along that longitudinal axis, the weight, the center of weight. Everybody should be able to just quickly grasp what's happening there, right? If the weight's too far forward, you end up with your CG way out here. You have a nose-heavy airplane. Bad, not as bad as back here. Okay? This is bad. This is awful. If I'm going to test pilot anything, I'd rather be a little this way than I'd rather be a lot this way than a little this way. Okay? All right. I really don't want to be either, but forward is the lesser of the two evils. So let's investigate that, or let's investigate the stability characteristics around the other axes. I talked about it a little bit, but we didn't really talk too much about it, so let's do that. We don't need that anymore. Okay. We have longitudinal stability. That's what we've mainly been talking about. And usually, when you do weight and balance calculations, really you are calculating the weight and balance along the longitudinal axis. In other words, you're evaluating pitch stability, longitudinal stability. You don't want to be tail heavy, and you don't want to be too nose heavy. You want the CG in the right place so that you're balancing in the right place, so that the sawhorse, if you balance it, is in a very tight little range where the manufacturer says it needs to be. You got to fall within that range, within the forward CG limit and the aft CG limit, whatever that range is, you want to fall between that. That gives us longitudinal stability. But let's talk about lateral stability a little bit, okay? With lateral stability, we don't calculate that, do we? And the reason is, generally, our airplane, when we're calculating that center of gravity, it's typically going to fall, you know, right in here, some kind of sort of in the middle of the fuselage. It's not falling out here someplace, right? Typically, okay? On single engine airplanes like what we're flying, the CG is going to stay pretty close to the center. Now, in the Remos, I will tell you that, let me draw a bigger kind of a picture, that you got the pilot sitting here and you got the instructor or the passenger sitting here, okay? Well, if I weigh 210 pounds and you weigh 150 pounds, the CG is not going to be right here. It's going to be over here somewhere. So as we're flying, the airplane is going to have a tendency to want to roll this way, but very slowly, because the CG didn't move this far, it moved this far. So that little bit of weight will cause it to roll a little bit. And how many of you that have started your flight training that fly with a heavier instructor have noticed that? That's what happens. In addition, the fuel tank is located right behind us, right here. So you have the weight of the fuel here, plus you have the weight of the instructor or passenger here. So typically, in these airplanes, the right side, or passenger side, is a little heavier than the pilot side, and so instead of the center of gravity being right between us, it's maybe just a little this way, okay? So the plane has a tendency to kind of do that a little bit. And then what you'll notice is when you're flying solo, when you get to your solo stage, the weight of the fuel offsets your weight, and it's typically more stable. And then you put somebody in there, it wants to roll a little bit that way. So what you'll find when you're trimmed out is every once in a while you have to kind of give it a little bit of left aileron to keep it from rolling to the right a little bit. Okay, that's what's happening there. But it doesn't get so far off that we have to really calculate. It's not so far off that we're in danger or anything, all right? But if you're flying an airplane, let's say that it has tip tanks, and you got fuel tanks right here. You ever seen planes with tip tanks? Okay. Well, now you can get an airplane that gets unstable in roll. Even airplanes that have fuel in the wings. Some airplanes will have fuel in the wings. You could have inner fuel tanks, you could have outer fuel tanks, and you could have tip tanks. So you could have fuel here, fuel here, fuel here, 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 and here. That can mess with roll stability. So now you have to think, if you're flying a plane like that, you have to think about how am I going to burn fuel? And generally speaking, what you do is you burn fuel from the outside in. Get the weight, get your moments, your big moments, and move them in. So you're going to burn from here and here, and then from here and here, and then from here and here. Equally if you can. Try and move it in. All right? If you fly something like Pipers, which are low wing airplanes, they typically have a left tank and a right tank. And there's no way to pump from both tanks at the same time. Unlike airplanes that have fuel tanks on the top wings, gravity can feed those down, and you can run from the right tank or the left tank or both tanks at the same time. So you end up with a balanced load. But when you're flying something with a low wing that has tanks on both sides, you'll recognize this when you start flying these planes. You have to time it. Every 15 minutes you switch tanks. Let's pull from this tank now. Let's pull from this tank now. That way you don't end up with a heavy wing. If you're flying the airplane without a autopilot, if you forget to switch tanks, you're going to recognize it sooner or later because you're like, man, I'm really having to do this. You know, oh, that's right, I've been burning out of this tank and I've got a heavy wing over here, or you're doing that. If you're flying with an autopilot and you forget to do it, and you turn the autopilot off, the airplane goes real quick and you remember it, okay? So just recognize that you can get your roll stability off. It can go off by, typically it's fuel loading in the wing, okay? But in our case, and that's why it's important to understand the fuel system when we do systems. Did you guys do systems while I was gone? Okay, you did systems already. Did they harp on the fuel system, how important it is to understand the fuel system? Okay. Yeah, so when you want to understand the fuel system in your airplane, not only because you don't want to run out of fuel, but because you want to know how to maintain weight and balance stuff. Not as critical in a plane like this, one tank, one valve, pretty much on the CG, doesn't have a lot of effect, but when you get in some other planes it could. All right. The other way that we maintain roll stability in an airplane from a design standpoint is, if it's a low wing airplane and sometimes high wing airplanes, by something we call dihedral. So when you look at this airplane right here, this Skyhawk, if you look at it straight on, you notice how the wings kind of tilt up? How they kind of go up like that? That's called dihedral. And if you ever look at a low wing airplane the same way, you don't see this, you see that. You ever notice that? How low wing airplanes have a large amount of dihedral and high wing airplanes have a small amount of dihedral? And then you can look at some fighter jets and they have anhedral. The wings actually go down, okay? So you can have a straight wing, you can have a dihedral or anhedral, okay? And I'm gonna explain what that means. It goes to stability. It's a design characteristic for the stability of the airplane. So in roll, if you take the fuel loading problem out of it and you just look at, if you assume your CG from a roll standpoint is in the middle or somewhere in the middle, if we want positive static stability and positive dynamic stability in roll, then that means when we bank the airplane, if we take our hands off, we want the plane to come back, right? We want it to right itself. So we want to design that into the airplane. That's what the dihedral is for, or on a high wing airplane, not as much dihedral. So let me explain. If a high wing airplane has no dihedral, and a low wing airplane has a lot of dihedral, I'll explain why. If this is my center of gravity, and this is my center of gravity, let's just say it's right there. When I bank this airplane, I'm going to go an extreme here. When I bank this airplane, this center of gravity, I'm pulling here. What's that going to do to that overall system? It's going to right it, because I've got that low CG, so picture this as the CG. When I do that, that CG pulls me back to a righting position. So the fact that I have the CG slung underneath the wing gives it some stability just from a pendulum standpoint. With this one, not so much. Now my CG is here, and it's pulling here. What's that causing? It's causing it to get worse. It's causing it to want to increase the roll. But because I have dihedral, this wing is generating more lift because its direction into the wind than this wing. And so this dihedral causes it to right itself. So with a low wing airplane, we need that dihedral so that when we bank, this wing actually causes, I'm going to get more lift on this wing, it's going to pull it up. When we have a high wing airplane, the fact that the weight is slung below the wing is a pendulum effect, and it kind of helps it out. That's why you don't see as much dihedral on high wing airplanes. You'll see some, but you won't see nearly as much as you do on the low wing airplane. So that's a design characteristic. So then we could say that with a low wing airplane or even a mid wing airplane, dihedral increases roll stability, right? Okay. But if we want an airplane that is unstable, we want a fighter jet, do we want stability? No, we want instability. So we sweep them down so that it's even less stable and becomes more maneuverable. So that's why you'll see that both on the wings and on the horizontal stabilizer. You'll see the horizontal stabilizer swept down, and the wings will have some anhedral to it. And that's a design characteristic to generate an unstable condition, which makes the airplane more maneuverable for dogfighting or whatever, and causes the necessity for to have computers flying the airplane, basically. Okay, that started, I think, with the F-14 Tomcat. I think that was the first airplane that had computer. I might be wrong, but I think it was the F-14. All right, another thing that causes roll stability is swept wing airplanes. So when you have a swept wing airplane, there's two reasons for the swept wing airplane. One is that it generates roll stability. It also, if you're flying an airplane that gets close to supersonic speeds, it helps with the shock waves. Yeah. So you'll see high-speed airplanes have those swept wings on them. So it does that as well as helps with roll stability. All right. Then with yaw stability, let's look at yaw stability. Just like in pitch stability, the bigger the distance between here and here, in other words, the longer the arm, the more stable the airplane is going to be, right? If I have this out here and I have that long of an arm, I have a really, really stable airplane. It's so stable I can't, it's a lead sled. It goes straight. It don't turn. It just goes that way, right? And the further back I go here, the shorter the arm, the more unstable it becomes, right? So the bigger this arm, within reason, and that's why you got to there's a range. That's why we have that range, all right? But the bigger this arm, the more stable it becomes. And it can become so stable that it's nothing more than a lead sled that goes in one straight line and you can't even turn it, you know? And the farther I go this way, the more unstable it becomes and the more I need a computer to fly it, okay? Same thing happens with this. So now let's look at the airplane from the top down. Here's my tail back here. Here's my wing up here, okay? Here's my CG. Here's my vertical stabilizer. My rudder, my vertical stabilizer. Here's this, remember, everything pitch, rolls, and yaws around the CG. So what's my distance from here to here? The longer that distance, the more yaw stability I have. If I put the CG way back here, that distance got shorter. And the less yaw stability I have, the more the airplane would want to tend to fishtail a little bit because I don't have a big arm back there. The further the CG is up here, the more stable the airplane would be, right? That makes sense? So it really is all about the CG, especially when we're loading the airplane. If you're not in that CG range, the manufacturer says make sure you're loaded in this range. Don't exceed the forward limit or the aft limit. Stay in the range. If you don't, you're affecting pitch stability and yaw stability. Not so much roll. You're not affecting roll as much, but you're affecting pitch and yaw. Okay? And it's because of the distance between the stabilizing force, either the horizontal stabilizer elevator for longitudinal stability or the vertical stabilizer and rudder for yaw stability. So wherever you end up loading that thing, that goes to how, do I have a statically and dynamically stable airplane? Neutrally stable or negatively stable airplane? Make sense? Okay. Questions? Comments? Concerns? All right.
On a Boeing, so.
On a Boeing,
Yeah,
like a big plane?
Yeah, how do they do the weight and balance on that, or do they just have a number and they're like, hey, you can't max this?
No, they do. You do weight and balance. You do weight and balance on every airplane. No airplane flies without doing a weight and balance.
Passengers have.
So what they do is, well, first of all, they have a much bigger range. Like on these planes, we got to, literally that's the CG range, and when you calculate, it's got to fall within a foot or so. With those larger transport category airplanes, that range is much, much larger, and the load master, you have a load master, okay, you have somebody that is calculating all this stuff, and that then goes to the pilot, and the pilot then has to sign off on that stuff. The pilot's not doing it in that case. There's someone else doing it. Dispatch is doing it. But they are taking how many people are on that airplane. They don't know what everybody weighs. They know what your luggage weighs because they weigh that. So they know what's going in the hull. And what they calculate right now, I think I think we use 180 pounds, 190 pounds. Every person, that's what you weigh. And they calculate that's what's going in every seat that's occupied. And then they can shift load in the cargo bay, what they need to do there if they need to. Yeah. But when you get in the smaller regional, have you ever been on a little regional puddle?
Not yet.
Okay, well, when you get on one of those, it's not uncommon that you sit down there. Okay, now why don't you come up over here and you move back there, and us heavy guys are going to the front and the light people are going to the back.
Yeah.
Generally speaking, you want the heavy stuff in the front and the lightweight stuff in the back. That's what you want. So if you're a little dude, you're going in the back. If you're a big dude, you're going up front. That's just kind of the way it goes.
Took a float plane from Seattle to the San Juan Islands, and it was about a 10-passenger float plane.
Yeah.
And these things are really wild. You're going to get a ride one. They took the biggest guy that they had in the plane, and they actually stuck him in the right seat.
Yeah, they'll do that a lot. Yeah. If it's a smaller plane like that, the heaviest person's going up front with the pilot.
Yep.
Yeah, that's pretty typical. Yeah. Yeah, because then you're pretty much right on the CG, right?
Yeah, we
So
were
then it's just a
we were
weight
pretty
thing.
fully loaded.
Yeah, yeah. Yeah, and if you get in like the Boeings or the passenger jets, and there's, like I've been on a few where there's, 20 people, 30 people on the plane, then they'll make you spread out. Because otherwise everybody wants to sit right up front, and then all the way, and they're like, no, just go spread out. We don't care where you sit, but spread out.
There's an airline pilot that said that a lot of the airlines, when they're calculating passenger weight, there's a mean that they use for men, and there's a mean they use
Yeah,
for women.
yeah,
And that's
yeah.
one of the reasons in your flight profile you have to select male or female.
yeah, yeah.
Because that's for weight balance.
Yeah, weight and balance stuff. All right, good. You guys learned anything new today? Okay. All right, so we got a couple of minutes here. I'll ask a few questions. See what stuck. Put your notes away. Okay. Yeah, just leave them on the desk. I'll pick them up. I'll pick them up later. All right. What's a moment? It's a rotational force. Yep, it's a rotational force. How do we calculate a moment? Weight times arm, okay. What's a datum? What do we mean by datum?
It's,
Measuring point from, like the point you choose to measure
Okay,
from.
all right.
it's just center gravity.
And that's how you, yeah, everything measures from that. So if you're looking at a diagram, you're looking at me at the diagram here, and the datum is here, and you have to put weight over here, what's the arm? Negative. If it's over here, it's gonna be positive. All the time, anytime. If you're looking at a diagram, and you're going that way, it's a negative arm. Going that way, it's a positive arm. So you'll end up with a negative moment or a positive moment. Sorry, looking at me, a negative moment or a positive moment. Yeah. Okay. All right. Somebody tell me what's the difference between static stability and dynamic stability?
Static stability is what happens initially after the change.
Okay.
And dynamic stability is what happens down the line
Okay.
after the change.
All right. All right. Let other people answer. You got all the answers. You've been through the class already. All right. That's good though. All right. What is? Tell me what. Let's see. Let me think about this. What is it that causes, primarily in the design of an airplane? How do we design an airplane to have positive static and dynamic stability longitudinally?
To keep the center of gravity slightly forward of center of lift.
Okay, all right, and that is true. And there's one other thing I also didn't mention, and it's my fault. I should have mentioned the flow patterns around an airfoil in general. The flow patterns around an airfoil in general cause a nose down pitching moment. So even when you take the center of lift and the center, so in other words, if you just look at the wing itself that's generating lift, it's going to generate lift like this is lift happening on the top wing, this is lift in the opposite direction happening on the bottom wing. So the wing, the airfoil itself has a tendency to want to do that. So along with where the CG's at. Good. All right. And how do we design an airplane design it? Now remember, we can screw it up with the way we load it, but how do we design an airplane, Maggie, for yaw stability, to be dynamic, statically and dynamically stable in yaw? In this direction, around the vertical axis. What's the important thing that's going on there? It's the last thing I drew up here. It has to do with the distance between what and what? The arm of the CG to the vertical stabilizer. Yeah. Yeah. And how much force I can get out of this vertical stabilizer. So if I designed an airplane, let's say I designed an airplane that looked like this. The tail will only have to be about that big. But if I design an airplane that looked like this, the tail will have to be that big. Right? Because tiny arm, big arm, right? So the force that needs to be applied, if I need the same amount of force, I need a big surface area because I got a tiny arm, or I need a tiny surface area because I got a big arm. That's true in both the horizontal and vertical stabilizers. In fact, designers call it a tail volume coefficient. There's a calculation to calculate the volume or the area that the tail needs to be, and it's a function of the distance of the arm. Yeah. All right. What's a station?
Distance from the datum.
Each spot is.
Position is positioning your company.
It's where you can put weight. Yeah. It's where you put the weight, what you calculate. The station is the distance. The station is where the arm ends up at. So from the reference to the end of the arm, that's the station. That's where you're putting weight. So the pilot station, passenger station, fuel station, cargo station, all that kind of stuff. Okay? All right. So now that you guys have been through this class, what I would encourage you to do, whether you've done this yet or not, next time you fly, next time you fly, let me grab something real quick here. Okay, these are sheets that everybody should be grabbing before you fly. Everybody familiar with these? Okay. So on these sheets, when you open it up, right down here is weight and balance. That's weight and balance right there. I would encourage you to start doing a weight and balance right there every time you fly. And what's on this, you can grab one when you leave off the table up there, is it says fuel 6 pounds per gallon. It shows you the arm for the fuel, seats, because there's only one set of seats, and the arm, and baggage, because there's only one place to put baggage. So it's very simple. You've got 4 stations really. You've got the empty weight of the airplane, you've got fuel, seats, and baggage. That's it. All right. So what you have to do to calculate the center of gravity is you got to put the weights in there, multiplying times the arm, and then just do what we did. And you can calculate the CG of these airplanes. And we have down here on the bottom, it says the maximum gross weight is 1,320 pounds. The fuel capacity is 21 gallons. The forward CG limit is 9.6. The aft CG limit is 16. So you can quickly calculate the weight and balance. I encourage you to just start doing that, right? What do you have to, where are you going to get the empty weight? From the airplane. Where in the airplane? The documents. The weight and balance, the AARO, Airworthiness Certificate, Registration, Operating Limitations, weight and balance documents. Where's the weight and balance document found in every one of our airplanes? In that little leather black book in the very back. You get it right there. You get the weight and either the moment or the arm or both. You only need one, right? Because you can calculate the other. Okay. Good deal. Next week is, what is next week? Yes.
So if you have you upgrade your GPS unit in the plane, or you add,
oh, that's a good point.
6-pack.
Okay, good point. Let me say that. I know where you're going. Let me say this real quick. So the weight and balance so I frequently ask, what do any of the documents, do any of the Aero documents expire? The answer is one of them expires. The registration expires every 7 years. However, the weight and balance documents, if you change something, if you add or subtract weight, then we either have to reweigh the airplane and calculate a new weight and balance document and put it in there, or we can mathematically do it. We can say I subtracted 10 pounds from here and I added 5 pounds back, or whatever it is, and you can do the math, but you still have to update the weight and balance document. That's your question, right? Yeah. Okay. All right. Next week, guys, is aircraft. Oh, it's aircraft performance. Okay. Next week is aircraft performance. So read that chapter. I think it's chapter 11 in the 8083-25. Read that chapter. Okay? All right. See you guys.